Well, good morning, everyone, and a very warm welcome to this week's CIBSE Grow Your Knowledge webinar, where we'll be discussing the what, the why, and the how for building controls. And just to clarify that in this context, today we are talking about building management systems and building automation. We're not discussing regulatory, statutory, or legislative building control processes. That was a question that popped up last night, and I thought important to clear off. My name is John Belfield, and I work for a system integrator down on the South Coast, designing and delivering building management systems. And on behalf of CIBSE and today's three speakers, can I thank you all for making this webinar your priority this morning. No matter where you are on your career path, whether you're just starting out or whether you're a seasoned campaigner, your involvement in this webinar and also in the newly formed CIBSE IT and Controls Group is absolutely critical if we are all to make the changes which we seek. So by way of a little update on the newly formed IT and Controls Group, it's already made up of consultants, manufacturers, systems integrators, and we've even got architects coming to the group. And it goes without saying that the more diverse the group becomes, the more effective it will be. So please do get involved as and when you're able. I'm conscious of time pressures, but your voice is vital to the success of this group. Just a few housekeeping notes I need to share with you. Firstly, this webinar is being recorded, and the presentation slides and link to the full recording will be sent to you via email tomorrow. I can also confirm that a CPD certificate of attendance will be included in another follow-up email, perhaps a few days later. And really, again, just to celebrate the Grow Your Knowledge webinar series, and just to remind you that all the recordings of previous webinars can be found up on the CIBSE website. It's pretty easy to find, but I'll just give you the address anyway. cibse.org/Grow Your Knowledge, and it's a terrific resource for a lot of information. So before we kick off the presentations, I was just thinking this morning, I recalled a conversation with Howell Davis a couple of years ago at the Build to Perform when we were discussing how the BCIA, the Building Control Industry Association, how they could work more closely with CIBSE. And Howell responded in his candid manner, and he said that CIBSE needs to bring BMS out of the shadows. CIBSE needs to bring BMS out of the shadows. It struck a chord with me. We've come a long way in the past 2 years getting system integrators and consultants more closely aligned. And continuing then on this journey, bringing BMS out of the shadows, let me introduce our three speakers today. First up, we have Peter McDermott from Mott MacDonald, who will start us off with what the building controls are. We then have Tom Hopton from Borough Happold, who will explain why they are essential to building performance. And to round off, we have Tom Randall from Ovara mapping out how these systems operate efficiently and how they can be delivered. We planned that each pitch will be around 10 minutes. We'll have the Q&A session at the end of the three presentations. So if I can ask you to post any questions you may have, you'll see a go-to webinar dashboard. We will get through as many of the questions you post as possible. So let's get started with what building controls are. Peter, over to you.
Okay, I'm Peter McDermott. Thank you, John. I'm the lead for BMS controls at Mott MacDonald, which is a large international consultancy. I've been in the industry for probably over 30 years now. I've worked for manufacturers, systems integrators, and latterly as a consultant engineer. I was involved in the CIBSE Guide H when it was first produced 20 years ago or so. And the chair of the steering group on that occasion was a chap called Jeff Livermore, who was Professor of Engineering at Manchester University at the time. He wrote a preface for Guide H, the original one, and it had some interesting comments in it. He said that controls were poorly understood in the industry, and that university courses became highly mathematical and were disliked by the students. So if anyone's lucky enough to have studied engineering at uni or college like I did, they've probably got vague memories of transfer functions and Nyquist diagrams and bode plots and a lot of very complex mathematics. I'm not going to go into that this morning. I'm going to just start with some basic concepts and their practical implementation, and we can leave the more complex stuff for the experts or maybe later events. So here's a picture of Wembley Stadium. If in the parallel universe where COVID hadn't dominated our lives, the Euro 2020s would have finished recently, and quite possibly England would have won their first major international trophy in over 50 years. That hasn't happened, so we'll just have to wait for next year to see whether that's a possibility. I picked this picture, partly because it's a very large building with very complex services, very sophisticated controls, and they're busily functioning, making that building work for the people that use it. But obviously the crowds that go there, they're not interested in what's going on behind the scenes. They're interested in the destination itself, the experience, seeing England win a cup final, or maybe Westlife or Madonna when they're performing at the stadium. So this is another stadium, but in a parallel universe, we'd be watching the Olympics in Tokyo, and again, a showpiece stadium, complex services, and complicated control systems behind it. No one's interested, and we only notice them when they go wrong. For instance, if the environment is wrong in the boxes, or the access control isn't working and the turnstiles don't work, or more seriously if there are issues with smoke extract or fire. So given that it's a necessary evil and no one really notices it, why have controls in the first place? So this is an example. It's a motor car. It's a complex mechanical and electrical system. If you didn't have any controls, what conceptually could it do? Basically, it could be stationary, or you could conceive of it being set up to move at a fixed speed in a straight line, and then there would be no need for controls. But obviously, both of those scenarios, the performance of the car is less than optimal, and therefore we need controls. We need a steering wheel, we need gears, we need brakes, so that we can modify how the machine works to reflect where we want to go and the environment around us. So in terms of buildings, we start with more basic manual controls. So I've just shown pictures of a light switch, shower controls, and a simple radiator valve. So we can use the light switch. It's intuitive. You push it on and off. The lights come on or off. The shower you can switch on or off. The valve, if you know what you're doing, you can adjust that to vary the flow of hot water into the radiator. So it gives you on-off control, and some of the more basic concept, it also gives you the ability to modulate it. So you may have a dimmer switch for the light, so you can vary the light intensity. The shower you can turn on and off, maybe vary the flow, and maybe mix the temperature. So all of those things, we're responding to what the user wants, and also to the wider environment. So is it dark? You wouldn't put the lights on if it's not, and maybe you might have a hot shower on a cold morning, but maybe before going to bed in very hot weather, you might choose to have a cold one. So you're reflecting the external conditions and the user desires, and just doing it using very simple manual controls. So we can get slightly more sophisticated. You need, for instance, with that shower control, I don't know if you've ever been into a gym where someone has been into the shower and not realising it was manual and just walked off and left hot water pouring away potentially for hours. So it's good to automate things if we can, and simple ones that we might see around the house are thermostatic controls, thermostatic wall sensors. They're just using simple bimetallic strips to switch systems on or off. The one in the middle is a pneumatic system for doing PI control. So this is, the way things were done and the way they can still be done. So here's a simple building services installation of domestic heating. We've got boilers, we've got radiators, we've got a hot water cylinder. And typically we would use thermostats around the building, possibly on the hot water tank as well, and maybe simple time programmers. So for the last 30 years, of course, the history of our world has been about the march of digital. As the microprocessors become cheaper and more effective following Moore's law, they've gradually spread their influence. So from about the 1980s onwards, digital controls were cheap enough to implement in buildings, and we saw the growth of direct digital control or distributed digital control. And what you would have here is an intelligent outstation or controller, which would then have a series of inputs looking at temperatures, humidities, switch statuses, fault conditions, and then doing some sort of calculations in the microprocessor, and then as a result of those calculations, starting fans, varying pump speeds, maybe opening and shutting valves and dampers and such like. This is just a picture of an installation, what it looks like in reality. They're typically installed in control panels. This is a typical controller at the top. These inputs and outputs here would be wired out through the terminal block at the top and out to various devices out in the field. And there may be various power supplies or relays to switch larger loads, electrical loads. Within those controllers, you have the software, the application algorithms that will take the inputs and then process them in certain ways, make decisions, maybe control outputs, and then they then act on the outputs. And one of the beauties of DDC is that you can configure this software to do complex stuff. You can change it as the building evolves, and maybe there's a need to change the way things are operating. So a series of these DDC, so each of these nodes at the bottom would represent one of those small computers or controllers connected onto the network. And then you have a DDC network. They can exchange information over a field bus or some other communications method. And if you stick another PC originally or a server-based system, that allows you to have a computer-based user interface, a BMS supervisor, or a graphical user interface, HMI it's called, human-machine interface in certain circumstances. So, as I said, probably 30 years ago, BMS was pretty much the only show in town because the microprocessors were adopted to control the HVAC, but then other systems in the buildings were developed, such as access control systems, CCTV systems, perhaps separate metering systems, lighting control systems, and each of those systems would have its own front end. Now, because they were designed by different manufacturers, the technology would be different and the way the information was presented would be different. That would be easy to, or relatively easy to implement in the construction phase, but very difficult for the end user to manage multiple interfaces with different technology. So one of the ways that was developed to overcome that was to integrate all of those systems onto a common bus or network, and then have a single seat IBMS, an integrated building management system, that would allow the user to use one interface to manage all those multiple systems. So in our industry, there is a plethora of 3-letter acronyms and 4-letter acronyms. I've just put some of the basic ones here. So the building automation system, the BAS, was typically what it was called back in the 70s and 80s, and still very much in North America. DDC is direct or distributed digital control, which is referring to those small computers around the building. BACS, building automation and control system, is the terminology that's used in Europe and therefore in a lot of European standards to refer to pretty much the same stuff. Building energy management system was a popular terminology in the 80s when the focus was on energy management. It fell out of favour and was replaced a little bit by building management system, where the view was on the overall management of the building and the energy just being a component of that overall management. It's found favour again now with the focus on carbon technology and energy saving. And then the integrated building management system is that kind of system that sits over all. So just a couple of slides to show what typically you might see on one of those interfaces traditionally. So you get a graphic that shows you real-time information. You could click on boxes as well. You may get pop-up alarms. This is the sort of typical standard, maybe 3D effects. This is very much can be tailored to suit the user's needs. This is focused really on an engineer to diagnose problems if the environmental conditions are not what's hoped for. So, and then the trend. One of the facilities that gives you is the ability to record and log data. So you can record temperatures or humidities in this case, and also valve positions and such like. So that's ability that gives you the chance to diagnose problems over a period of time, and is very useful for instance, for loop tuning and such like. So you can compare different actions and the impact, and that allows an engineer to sort out problems. So one of the concepts I just want to introduce is that in traditional design, the MEP engineers, mechanical, electrical, public health engineers have a very challenging role in fitting all those complex services into the building envelope and maximising the amount of space that's available for the usable things like the sporting activities or the office work. Typically, we might design for boundary conditions in the UK of maybe 32 degrees, and we might have to design the cooling systems to bring down the internal environment maybe to 24, maybe to 21 if that's the user brief. So all of the systems are sized, the chillers and the pumps and the pipe work, to achieve that worst case scenario. And likewise for the heating, we might design for -4 as a design parameter, and we have to provide boilers or heating or air source heat pumps or whatever, and all the pumping and the pipework that goes with it to bring it up to 18 degrees. Now, -4 and 32 are very unusual weather conditions in the UK. So for the vast majority of the time, the systems are all working at part load, and this is where the controls are vital, because if the controls aren't designed correctly, then you don't get the right environments for most of the time. So I'll just posit this as one way. The traditional design process focuses on meeting those boundary conditions, and then it sees the systems design as sometimes a contractor design portion, but certainly as an afterthought. So what I favour is working the other way around, which is looking from the user's perspective at the systems that they will use to interface with the building, and then making sure that those are built in as the design progresses. So that's my piece, and I'm going to hand over now to Tom, who's going to explain a little bit more about why these controls are ever more important.
Thank you, Peter, and really great summary of what a BMS is, and also really great to see so many on the call. I am going to be covering the why controls and building management systems are now more than ever becoming so critical in what we do as designers, contractors, and operators of the built environment. I work at Bureau Happold, and I lead our smart buildings and controls discipline. And my agenda and what gets me out of bed in the morning is quite simple, really, to create better buildings for people, place, and planet. And controls is such a fundamental part of what makes a building perform better. And let's face it, as an industry, we could be doing better in this discipline. Controls has been considered by many as a dark art for too long, and perhaps through lack of understanding and expertise in our industry, controls have consistently appeared on industry lesson learned reports. And that's a cycle we need to break. And so I'm just thrilled to be talking today with John, Peter, and Tom to raise the profile of controls, bring the discipline out from the shadows, as kind of John mentioned earlier, and deliver better buildings. I'll make this slide work. So unprecedented has been the phrase for the last few months as as COVID has and continues to affect our way of life. Buildings accommodate us wherever we are, whether that be at home, work, or in our social activities, and all the pit stops in between. So COVID has put a lens to many of the trends that have been around for some time. Health and well-being has always been an important consideration, but it's top of the agenda right now, and bringing with it new attitudes to healthy buildings, which will likely stay with us for some time past COVID. So monitoring more parameters relating to indoor air quality, enhanced ventilation, UV filtration, and many more features enabled through controls help us build out our resilience to COVID. And that's a positive acceleration of that healthy building trend. But as COVID passes and its shadow lingers, we must look to controls to create adaptive buildings that can be healthy, but do so whilst being resilient to the second wave of the economic recession. And the third wave there, potentially the largest wave of them all, is climate change. And it sounds quite placid to compare to the others. Climate change, it doesn't sound like it's an unreversible change to our way of life on this planet, but it is a really very real threat to our existence as a human race. And we shouldn't think of that as being a debate. It's the forecast. And so taking control of our buildings, making them adaptable, making them highly efficient is the challenge we must all rally to support. So there are many pieces to that grand challenge. And I believe technology and how controls in our building management systems are designed, procured, commissioned, and operated are a key piece. Reducing energy demand is key, but creating systems which are intuitively controlled, environments which make people more comfortable, productive, where space is more effectively used, and systems which support efficient and effective building operations is vital. It's vital that we build resilience to really quite unprecedented challenges in our industry and ultimately move to a low or zero carbon economy. So we don't have all the answers now. We do know we need to accommodate change, and change driven by corporations striving for greater efficiencies in operations, but also business effectiveness and landmark shifts in national and regional government policies towards that net zero carbon future. And also, buildings exist for many years, and it's about 80% of buildings existing today will still exist by 2050. And so building refurbishments, they may be done a few times over the life of a building, and the control hardware, if we're lucky, might change every time we do a refurb. But these periods, the software hardly ever gets updated. And that needs to change. We as designers and operators need to plan to change and recognize that change is a continuum, because look how fast technology changes. And as it does, it becomes more commoditized and cheaper. And so, yes, we need to respond to immediate needs, which might be to reconfigure a space or upgrade a system. But in doing so, and in the gaps in between, we should keep moving towards operating our buildings, running our building management systems on the latest technology, the latest software, and programming, and that may be machine learning algorithms, it may be artificial intelligence. All these things will help us move against our longer term strategy of that net zero carbon future. So it all comes down to building performance. And that's a broad spectrum of technology that monitors and controls. It starts with getting the use of space optimized, and that technology might make data available from similar buildings to inform their layout of space, all the way through to the operational needs, and to be able to monitor and therefore adapt to changing user needs of the space, as well as systems which can dynamically respond to space use. But then to is about the environment and how it can lead to better health, well-being and productivity. And 3 is about how we organize our activities, building systems and business processes that are integrated and organized more effectively, which can lead to better user experience and therefore productivity. And these top-line benefits are about business performance, and we believe true sustainability is not just about carbon per square meter metrics, which is somewhat of an arbitrary benchmark, but instead should consider how productive a building is in its outputs. So the value of what we do in controls and in building management design should push up the top line as well as push down the bottom line. And lots of really useful guidance out there already on how control systems can lower energy use, and Tom Randall will cover this in more detail later. But not to forget that there is another bottom line aspect around FM and the way that we manage buildings. And that is both financial and carbon. It's how we organize our sensors and controls and BMS programming to minimize the effort needed to manage our built assets. So when we pay attention to controls and building management systems, we can find value and identify really quite high return on investment across the spectrum of building performance. So there is a more holistic value stack that I would like to table here. And in many ways, I feel the industry has lost sight of the full value that this discipline can bring. A rather flippant statement, but yes, there are good examples in industry, and in my opinion, there are many more mediocre or even poor examples of BMS and controls design. So we need to start with good foundations. Foundations of education, visibility, trust, and collaboration, and build up from that better consultation. Designs which consider the full value stack, designs which are extendable, flexible, reliable. Absolutely, they need to be efficient in carbon and cost, but they need to be better at supporting FM and do that whilst getting the most out of the top line of our buildings. I personally think that we need to rethink our approach in this discipline, the way in which we consult, the way in which we procure designs, and the way we manage contracts, and also acknowledge that there is a skill gap in consultancies and in the BMS industry too, which in the moment I feel is leaving us with outline performance specifications and a contractual framework where competitive tenders and program pressures squeeze the value throughout the process, but crucially in that commissioning phase where all the value is often missed under misplaced kind of B initiatives. So Tom Randall will be covering the how in more detail, but just to note there is guidance and there are processes that we can follow. And this is the output from a process we follow to justify and protect the energy value in a control design. We built a tool from the basis of a British standard, BS 15232, which I think is extremely valuable but severely underutilized in our industry. It's used to benchmark the energy performance of a controls installation, not just HVAC, but lighting and automatic blinds too, and really protect the value in a controls design by justifying the energy return on investment and protecting it from that so-called misplaced VE exercise. And this is another example, this time taking a diagnostic approach. Buildings generate vast amounts of data. This particular project had nearly 20,000 control points and time series data in excess of 1.6 billion. And so we need new techniques, data management techniques, to go hunt in amongst the data that is generated by our BMS systems to find improvement opportunities in comfort, energy, and maintenance. And this particular building performed extremely well. It was in the top 3% of similar buildings, but an almost forensic, almost diagnostic look at that data and the control programming allows us to identify the true ceiling of optimization, and through cost and carbon savings justify the interventions needed to achieve it. And on those interventions, provide clarity against each opportunity, moving from understanding energy consumption to quantifying the opportunity and crucially what we need to do. With greater understanding of controls, the behavior of systems in operation, and an understanding of the data that they produce, we can realize the full potential of optimization and really take strides forward to close the performance gap. And so this, in many ways, is a call to arms. We need renewed attention in our industry to this discipline. Ensure that the systems are optimized from the start and looking not just at energy consumption, but the whole value stack. So our building control systems can deliver a healthier, more productive environment, help FM deliver a more effective and efficient service, and do all this with the lightest touch on our planet. I think Winston Churchill said it best, we shape our buildings and afterwards our buildings shape us. So at this point, I'll leave you in the good hands of Tom Randall to delve a little bit deeper into the how to make a building management system perform. Thank you.
Thanks, Tom. Right, let's just get this up. Okay, great. Great. So, I'm Tom Randall. I work as an associate director within the Building Performance and Systems team, and sort of my journey actually started off as a BREEAM assessor, helping to shape at the design stage the design of building in terms of sustainability issues, and then sort of got into the whole performance gap agenda. Worked for a building management system analytics company, which then exposed me to the reality of the power of building management systems and control systems, but as has been touched on by the others, how frequently at the moment they're implemented in a way which means that buildings are not performing anything like as well as they could. So that's what I'm just going to give a good overview of. So in the first instance, I think it's worth dwelling a little bit about what we mean by building performance. So I look at it as essentially as an efficiency equation. So if there's an outcome that you want, which the others have built on, Tom talking about health and well-being, productive, comfortable environments, and actually by extension, for some, increasingly, that then reflects sort of investment value and investor demand. So there's a lot of high-value stuff at play here. And then it's delivering that functional outcome efficiently, in simple terms, as lowest cost. It's not just about energy. If you want a low energy building, that's easy. Turn everything off. So in relation to building management systems, and certainly looking at what the core of what they tend to look at, it's about delivering the right amount of heating, cooling, ventilation, frost protection, lighting, but delivering that in a low cost way, and of course including sort of an energy efficient, low energy way. So it's about achieving sufficient demand efficiently. So thinking about those two, demand and supply, a little bit more, like sufficient demand. Sufficient for me is a really important word here. It's about meeting, clearly not too little, but not too much. You can provide sufficient heating, sufficient cooling, but if you oversupply, you'll then actually again causing a problem. And the other thing about sort of making sure you have sufficient demand is making sure that your controls aren't sort of unintentionally setting up extraneous demands, which we see a lot of, notably fighting between heating and cooling systems. And so one part of the control strategy is setting it up so the delivery is sufficient, not too little, not too much, not extraneous demands. And then the next bit of it is working out how you supply that sufficient demand as efficiently as possible. So you might have several options available to provide cooling, for example, which I'll come into, which is the most appropriate one to use. And if you've got one that's got quite a complex system behind it, pumps and multiple chillers, whatever, what's the most appropriate way of operating that system in terms of temperatures and flow rates, which I'll come on to. So expanding that, just looking at the three sort of key services that building control systems cover in terms of heating, cooling and ventilation under the banner of sufficient demand, efficient supply. So in terms of sufficient, ensure that the delivery temperature is appropriate for what the building needs. So an example here is air handling units. You see many that are operating at a fixed supply temperature, which will inevitably result in situations where at different times of the year you're heating up the air and then cooling it back down again, whereas varying it in response to the needs of the building would be more appropriate. And then in terms of avoiding extraneous demands, which that last example actually includes, but another major problem that we see is where terminal units, fan cores or fans or whatever, supplying an open plan office are fighting with each other, and that's usually because one has a heating set point that conflicts with the neighbouring cooling set point. And something that Peter touched on, so the dead band, if you have a temperature set point of about 22 degrees, the dead band is how much that the temperature can float. So increase, for example, until cooling comes on, or decrease before heating comes on. The gold standard for offices, by example, the British Council for Offices, allows that to drift by plus or minus 2 degrees. So in that respect, the dead band is 4 degrees. But quite a lot of the time, even in open plan offices, you see spaces trying to be controlled to such precision that it creates these conflicts and ironically creates complaints, because somebody's sitting under a unit kicking out heat at 100% and somebody's sitting under a unit kicking out cooling at 100%. Looking at the efficient supply, I think cooling is a great example here. It might be, even if some, say, mechanically cooled building, it might be that actually just running the fans or even running them at night time alone to where the air is cooler, and night purging is a very efficient way of providing cooling. If you need a bit more cooling, it might be that the air coming back out of the building is enough that you can use your heat recovery systems to recover some cooling capacity. And then if that gets exceeded, it might be that then the mechanical cooling steps in, so the chillers, the cooling towers, etc. So the cooling strategy needs to be making sure it's selecting the most efficient option available for that demand. Once you've picked a system, particularly when you get into a more complicated mechanical system, look at how the system temperatures within that, so the temperatures at which the water is being delivered from the chiller going to the terminal units and the air handling units and coming back, the rate of flow of water within those systems, how those chillers are staged. There's a lot of efficiency can be achieved by paying attention to optimizing that configuration. And one thing to flag here, it's very much a discussion between control strategy and the engineering design. How much you can control sufficient demand and efficient supply is going to be also limited by the physical limitations of the building services installed. So there really needs to be a dialogue between the controls designers and the mechanical engineers so that they understand that. So for example, if you have a multi-story building where levels of occupation vary across floors and it makes sense to vary ventilation by floor, you can only do that if, for example, you've got automatically controlled dampers to each floor. If you don't have that, then providing sufficient air to each floor is just a non-starter because the right equipment isn't there. So it's very much an iteration. So the next thing is about usability. And a lot of the reasons of underperformance are because people are confused, frankly, and confounded by the controls that they're presented with. And two key sort of use cases, to use sort of the language of the software world, is your sort of lay occupant. You know, they might be going around in a building and they might see sort of on the left-hand side a panel on the wall, which to them is completely bamboozling, and will immediately undermine the ability of them to interact with that control system. But then similarly, for example, for an FM manager, what's on the right, it's a bit sort of, you know, it's not very pretty, but this is an example of how views can be created on the supervised screens that Peter was talking about. Most of the time I look at an existing building management system, that computer that gives you a window on what the system is doing, usually you can sort of look at each individual bit equivalently, but there's usually very few summary views that would give a facilities manager a lot of power to drill down into where the problems are. So this is actually an example of the screen that I produced for a client, where on a single page it's just summarising what's happening at the north and south zone across several floors. And there are a few things here that just means that if there are problems, they just really stand out. So in the middle, you've got how many zones in that building are operating at set point temperatures that are out of the expected standard. There's a big number there, then there's likely some sort of problem with how people in that space are experiencing it that can be addressed. Similarly, you can pull out whatever the highest or average heating and cooling demands are. And again, if you've got floors where you're seeing very high, cooling demands and they're maxing out to 100%, then there's very likely an issue. And then sort of final thing is to just consider about professional responsibility. Everybody is declaring climate emergencies. Everybody is saying we need net zero. And as has been covered by my colleagues, building controls are central to whether or not this is achieved. And as Tom has pointed out, there's lots within the existing way that BMS control systems are procured, which actually undermines their ability to deliver what they can. But if you look at the top of the tree, most of the clients you're working for are asking for this good performance. It's just the systems and things such as the current approaches to value engineering undermine that. And to a degree, sort of, we believe there's a professional responsibility for those involved in the controls to sort of pipe up a bit more and say, look, you are fundamentally undermining something that the client is committed to or that our profession has committed to. And they're tough conversations, but they're ones that we need to be more prepared to do. And then similarly, from a demand end, my colleagues in the Building Controls Industry Association, of which John's been very much part of, have established an apprenticeship scheme to increase sort of the baseline level of professionalism and expertise within the controls industry. And on that, I will hand back to John.
Well, thank you, Tom, Peter, and Tom. It's and just on everybody's behalf, you can hear a lot of passion in the voices here. There's a real, and I think it was Tom Hopton has said, this is a call to arms, and I feel that, I sense that as this community is coming together, there's a real desire to do things different, to do things better, and so I'm going to very quickly turn to get some questions in, because we do have some time, and they're popping up in front of me now. But if I can just start the ball rolling with this one.